So let me introduce Debasish. I work with Debasish at Lightbend on the fast data platform team and some other teams. Debasish has a couple books published under Manning. He specializes a lot in good functional and reactive API design principles, and he's frequently involved in a lot of API design discussions for Lightbend libraries and open source projects and commercial products and things like that. He's our go-to person. So it's really great that we have him to give this presentation. I think this might be the first time he's delivered this presentation. He'll let us know, I suppose. And what else? I was going to say something else. I guess that's it. Debasish, you want to take it away now?
Yeah, sure. Thanks, Sean.
Yeah.
So I'm Debashish. I'm one of the principal engineers at Lightbend. And as Sean mentioned, I love pure functional programming. And I have been doing this since quite some time now, I guess. So yeah, in my recent past, I have worked with complex domain models and how to apply the principles of functional and reactive programming as part of domain modeling. And as all of us know, that one of the challenges in delivering complex domain models in the functional paradigm is to handle side effects and how we can model them algebraically. By algebraic, I mean the pure referentially transparent way where we can reason about things. So, and this talk is an attempt to formalize that. Yeah, this is the first time I'm giving this talk. I'm supposed to give a similar talk next month in one of the functional programming conferences in Bangalore in India. And this is the first talk that I'm giving on this effect management in domain models. And at the outset, I'd like to mention that this is my first remote talk, so I'm not very sure how well it will go. What I think is that delivering a talk without looking at the reactions of the audience is always a challenge. So fingers crossed. So I'd like to start with the motivation of this talk. What exactly motivates this talk? And if there's one thing that you would like to take away with you once the talk is delivered, what is that? We always talk about the goodness of pure functional programming, programming with values, functions that behave like the functions we talk about in mathematics, where the output depends only on the inputs and things like that. We talk about equational reasoning. So by equational reasoning, I mean that you can use functions just like equations, just like as we do in mathematics in order to verify some of the invariants of your system. And we talk about lawful abstractions, the laws of abstractions which need to obey in order for your system to be consistent across all the bounded contexts. But the real challenge when delivering complex domain models is that in a complex domain model, side effects are plentiful. We have database interactions. We need to communicate with external subsystems. We have lots of I/O, etc. And all of these are inherent side effects which cannot be modeled in an algebraic way. But of course, we want to have all the goodness of this purity in our models so that we can reason about our model till the end of the world. So there are really 2 points to note here. First of all, does this really work? Or if it works, how it works in the presence of side effects, the algebraic model of domain modeling? And does this paradigm scale? We have seen lots of pure functional programming examples in blog posts and small articles and things like that. But when it's a real world domain model, I find it really challenging to model side effects in an algebraic way. So in the next 1 hour or so, I will be discussing some of the strategies that we can adopt, some of the things that we can implement in order to make this in order to make the impact of these side effects as less as possible in designing domain models. Some of these things will be familiar to you, but let me start with some of the basics. Referential transparency is one of the cornerstones in designing pure functional abstractions. And we call an expression referentially transparent if it can be replaced with its value without changing the behavior of a program. What does it really mean? This is known as the substitution model. For example, you have a function. You can inline the function body in places where it's invoked, and yet the program does not change in behavior. Then we call the function referentially transparent. So referential transparency is all about goodness of functional programming. And no wonder we call this model expression-oriented programming, because all of the expressions that we are dealing with are pure and referentially transparent. Unlike in imperative programming, they are not side effecty. And we talk about expressions as something that reduces to a value. We have a computation, we have an expression, and at the end of the world, when we reduce this expression, when we submit this expression to the runtime system, it reduces to a value. So this expression is pure. And the basic idea of programming with side effects is that we would like to make use of such expressions as much as possible, as opposed to side effecty statements. And as I was mentioning, we call this the substitution model of evaluation. Consider this example. This is a function which is referentially transparent. The output of the function depends solely on the input and nothing else. We don't have any external side effects, any dependency on any external systems, and we can compute the result of the function solely from the input which we give it to it. And contrast this to this scenario where we have a function foo which takes an iterator, and obviously this is not referentially transparent. When we replace a with foo, in that case we get a different result. This is because the iterator is maintaining some shared mutable state underneath, and this function is not referentially transparent. Now here's one more example. It's somewhat similar, but it demonstrates one important aspect or one important benefit of referential transparency. Here also, when we inline the function, the referential transparency breaks. But note in function foo, we have a plus b. In this trivial example, a and b are integers. But in real world, we may have some real complicated stuff, complicated abstractions as part of a and b. And if the referential transparency breaks, as in this case, in that case, we cannot reason about a and b separately. What we call local reasoning. If a is a complex abstraction, in that case, we may want to deal with a separately and try to understand what exactly is going on within a. This becomes easy if a and b are referentially transparent expressions, but they are not in this case. So referential transparency is not a compositional. Sorry, violation of referential transparency is not compositional. It hinders local understanding. We cannot locally reason about A and B without considering them together. And I think one of the greatest benefits of referential transparency is that it enables you to locally reason about your code. You can reason about abstractions separately and then combine them together to form a larger abstraction. And this brings us to the topic of side effects. In one of the presentations, Rob Norris mentioned that we have two types of things. One of them, on one side, we have referential transparency, and anything that breaks referential transparency is a side effect. Side effects are non-compositional. They are non-modular because you can't reason about side effects in a modular way. You need to consider the whole system as a whole in order to make any meaning out of it. And some of the examples are shared mutable state, database write, reading from standard input, interacting with external resource, and there are many other examples. But the matter of fact is that side effects are ubiquitous. You can't really avoid them. And whenever you are designing any system, you need to consider side effects as part of the model. So the question is, how do we deal with side effects in functional programming? They break modularity, right? They break referential transparency. Hence, we need to handle them somehow within the realms of our type system. so that we can still work with pure values till the end of the world. We need to defer the execution of side effects till we submit the entire computation to the runtime system. We'll see how. And functional programming is all about pure expressions, as I was telling, while side effects are all about statements and actions. Actions do mutate stuff. So we need to defer the realization of such actions as late in the life cycle of our program as possible. Now, here's one way how we can defer their execution. Instead of executing an abstraction then and there, what we can do is we can lift all actions into a container-like data structure. So we have the entire computation, but we haven't yet executed it. So till the time we haven't yet evaluated it or executed it, it's still a value. And we will see that how the type system in Scala offers us ways to achieve this. And this is the crux of what we call an effect. This container-like thing on which we can put our entire abstraction and defer its execution is what we mean by an effect. And we will see how to realize effects in the Scala type system. Now, this is a simple example of a bunch of functions which are supposed to be pure because the type signatures don't indicate that there's any impurity. I'm assuming that if there is any impurity, then the type information will give us that, though it's not mandatory in Scala, but it's always a good practice to have it as part of your type system. These are a bunch of functions which combine nicely together to give you the tax on the salary of an employee. So all is good when it's pure, when the functions are all referentially transparent. But what's the real challenge? The real challenge is to program with pure values with the same semantics of algebraic compositionality in the presence of side effects. The red box is the most important part. We want to have the compositionality. We want to have the purity. We want to have referential transparency, and that too in the presence of side effects. How can we design our system so that the impact of side effects is reduced to the minimum, and we can decouple the side effects from the pure parts of our program and have most part of our program as pure values, so that we can do equational reasoning, we can reason about our code, we can write tests. Pure functions, pure abstractions are easily testable, they're modular. So we get all the goodness of modular software engineering when we program with values and pure abstractions. And the tool which we have for doing this, one of the tools, the main important tool, is the type system, or rather the algebra of types. Types are algebraic in the sense that we talk about the algebra that we can count the inhabitants of the types, meaning how many instances can be there for a particular type. For example, in Scala, when we say a type is unit, we have the number of inhabitants is 1. With Boolean, it's 2. Take the example of a function. We have a function from A to B. What is the if we have A as the count of inhabitants of type A and B as the count of inhabitants of type B, then this function type has the number of inhabitants equal to B raised to the power A. Similarly, we can do lots of computations on the types with more advanced types, like if we consider the inductive types like lists and trees, there can be some more interesting computations and algebraic computations using them. We can even compute the derivatives using zippers, but that's something that's not relevant to today's discussion. The one aspect regarding the algebra of types which is relevant in this discussion is the algebraic composition of types. Composition lets us refine the algebra of types of our domain model and help us move towards the desired level of abstraction. What I mean is, suppose we have a domain behavior modeled using a function A to B, and one more domain behavior which is modeled using another function which is from B to C. Now look, the types align here, A to B, B to C. So we can compose these functions together to get a larger domain behavior. So in technical terms, we call this closed under composition. So whenever we compose a larger functions out of smaller ones, that larger function implements a more complicated domain behavior than the smaller ones. This way, we build our abstractions gradually and incrementally. And as I was telling that algebraic composition helps us move to the desired level of abstraction to the model. Compose like anything till you reach your desired level. From algebra of types to the algebra of a domain model. Now it's time to scale up. We have seen the algebra of types. Types are compositional. So can we say the same thing about the algebra of a domain model? But before that, what exactly is a domain model? Possibly the most important context, most important aspect of a domain model is the most important concept of a domain model is that of a bounded context. Any non-trivial domain model has multiple bounded contexts. And a bounded context is an independent subsystem within the domain model. And within a particular bounded context, we have a consistent vocabulary. The ubiquitous language, as Eric Evans mentioned in his domain-driven design book. We have a set of domain behaviors modeled as functions and domain objects implemented as types. And these behaviors have definite algebras. And each of these behaviors also honor a set of business rules because all we are trying to model is a business. So the behaviors need to honor the domain rules. And for modularity's sake, we can group related behaviors as modules. So as you see that we are moving up the scale of abstraction. We started talking about types. We then started talking about domain objects modeled as types or domain types. Then we started talking about domain behaviors, which is a mapping from one type to another. And now we are talking about grouping related behaviors into modules. So loosely speaking, we can say that a domain model is a union of a bunch of bounded contexts. Each bounded context is a composition of a bunch of modules, and all of these modules are typed. And every module consists of a bunch of functions. These are the domain behaviors. The functions model the domain behaviors on objects of various types. And functions compose with each other. And as I was telling, the functions are closed under composition. So when you compose two domain behaviors, you get a larger one. And these functions honor a set of business rules. So we have the functions, we have the types, we have the composition, and we have the domain rules. If we take all of these together, we have the domain model algebra. So when we are talking about a domain model algebra, remember this relates to a specific bounded context. An algebra is consistent only within the scope of a single bounded context. Across bounded contexts, algebras won't work because the subsystems are independent. The ubiquitous languages are independent. So we talk about domain algebra as the algebra of a specific bounded context of a domain model. So we talked about domain model as being a union of a bunch of bounded contexts. Now we can replace the term bounded context by domain algebra. So a domain model is a union of a bunch of domain algebra. That's how we would like to visualize it. The two main concepts on which we will base our domain algebra are the referential transparency and the compositionality of abstractions through compositionality of types. These two, if we can utilize these two aspects, these two will take us up the ladder of abstraction and help us design compositional domain models. But the question is, what about side effects? How do we model them? So irrespective of how we look at a domain model, repeatedly we are coming to the same question. How do we model side effects as part of the domain model? Now let's take an example. This will give you some intuition. Here we have a function which takes some input and it computes the salary of an employee. And obviously, as part of computation of the salary, it has to look up the database for all the information related to the employee in order to compute the salary. The first thing that strikes out from this function is that it conflates two things: the specification of how we compute the salary and the execution of that computation. There's a definite algorithm that needs to be followed in order to compute the salary. And finally, when we have the algorithm, we need to realize it by submitting it to the runtime system, when it will do the actual interaction with the database and compute the salary. The specification is the reification of the computation part. Here we don't have a separate abstraction that abstracts the algorithm of computation, that abstracts the computation in its unevaluated form. So what we can say is that if we can separate the two steps that we are conflating here, if we can separate the specification from the execution, then the specification can potentially be reused, right, with other abstractions. We can take out that specification of computation of salary. It's something like the recipe. We have one recipe, we have another recipe, and we can compose the two recipes. And the basic idea that we need to follow in order to make our abstractions pure and decoupled from side effects is to break this conflation, is to have a pure decoupling between the recipe of computing the salary and the actual computation of the salary. So here the first function, the compute salary, in the step 1, it only computes the recipe of how to compute the salary. It doesn't give me the salary. It gives me an IO of salary. You can think of IO for the time being as the container type. IO is the container which contains the recipe of computing the salary, which when submitted to the runtime system will give me the actual salary for the employee. And that's done in step 2. Excuse me. So in step 2, when we submit this abstraction to the runtime system, we get the side effects. So we cannot avoid the side effects, but we can defer it. And we can have a chunk of code which is not side effective, which is pure, and we can decouple it from the runtime system execution. One of the important things to note here is that since we have not executed the computation in step 1, we don't have a salary, right? And as I was telling, the IO is the recipe. But at the same time, IO is also the pure value. So this is an example where we have extracted the recipe, where we have extracted the computation and reified it in the form of a separate container-like abstraction. And the most important part of it is that it's still a value. So this is the intuition that I was talking about. We first create a function that takes the input arguments and prepares a description of the computation. And in the next step, we submit the description to the runtime to perform the execution. So step 1 is referentially transparent. Step 2 is not. Here's a simpler example of how to do this. Here, hello does not print hello. Instead, it creates a recipe which, when submitted to the runtime system, will let me print hello. Here's the same recipe for world, printing of world. Look how we can compose the two. Compose the two abstraction to form a larger abstraction. It's actually a larger recipe for printing hello world. And we can continue it like this. We can compose more abstractions along with this. So note that if we had printed hello in the first place without putting it inside the container, in that case, composability would have been lost. But since we have prepared a value out of this computation, the recipes can be composed depending on the denotation of the effect type. Here, IO is the effect type, as we will see later. So depending on the semantics of the effect type, depending on the denotation of the effect type, we can compose them together. For example, IO is a monad. So IO being a monad, the denotation is that of sequentiality. So when we compose the three things, hello, world, and hi, in that case, we have a recipe where these instructions will be executed in sequence. So we will get a printout of first hello, then world, then hi. And the final step is the one which interacts with the runtime system, and this step actually does the printing part. So the basic idea is to abstract side effects into type constructors. IO is a type constructor. IO is a parameterized type to which, when we give a type parameter, it actually becomes a type. But till then, it's a type constructor. So we need to abstract side effects into type constructors. And these type constructors, we call them the effects. Here are a bunch of effects which we see in daily life. Either AB is the disjunction effect. The partiality effect is option. We can either have a value or we don't have a value. But so long it's encapsulated within the option, it's still unevaluated. Only when we take out of it, we get the actual value. Reader monad is a way to read from the environment or implement our familiar dependency injection pattern from object-oriented programming. But in this talk, we will mostly focus on the IO part of it, the IOA. And if you look a bit into each of these abstractions, you will find that it has a general shape. The shape is FA. We call A is the answer that the effect computes ultimately when we submit it to the runtime system. And the rest of the computation is the F part. We still don't know yet what F means because F is still opaque, right? F doesn't have any denotation. But F is the additional stuff modeling the computation, which means that this entire recipe thing that I was talking about, lifting the pure value into a recipe, and then finally submitting it to the runtime system with all the semantics is the function that F does. But till we give F a denotation, F is an opaque type. It has no denotation till we give it 1. But the interesting idea is that if we keep F as it is, we can make it polymorphic. If we fix IO for F, in that case, we can only use the IO kind of effect. But someone may decide to use some different effect for F. For example, they may want to use the Monix task for handling effects. They cannot do that unless we keep it parametric. So we'll focus mainly on the IO effect. It's tricky and has to deal with the edge case of your program because that's where it interacts with the runtime system. And obviously, it's one of the common requirements of domain modeling, interacting with databases, message queues, external subsystems, etc. And we will see how we can deal with IO polymorphically. Now let's start to design some domain abstractions. This is an algebra, just the contract of an account repository. Repository is an abstraction is an artifact of domain-driven design, which abstracts the access to the database. You can access an underlying store to fetch your entities and values and stuff like that from a repository. So we are considering a system where we have some bank account, and account repository gives us the algebra or the contract for interacting with the underlying database of which stores account-related information. As we see that each of the APIs are effectful, we have indicated it with IO. So query gives us an IO of option account. Store stores the account, but the return type indicates that it's an effectful operation. So it's effectful, but as I was telling, it's concrete. On behalf of the user, we have made the decision that the effect type will be IO. This works with smaller models, but with larger models, when you need to interact with multiple artifacts and you need to compose effects, have polymorphic effects. Under these circumstances, it's always better to keep the effect type opaque as part of the algebra. So this is an example of the APIs being effectful and parametric. Parametricity has lots of benefits. The moment we replace IO with M, we are taking away a lot of knowledge. We are taking away a lot of specific information from the contract itself. We are making the contract parametric. Parametric means more generalized, right? M is more generalized than IO. We really don't know anything about M. So that if the algebra specifies M, in the implementation part of it, we really cannot assume anything about the specific type of M, because there is no specific type. It will depend on what type you instantiate it with. So it's more generalized and less constrained. Hence, we have lesser number of possible implementations because we cannot assume anything regarding the type of M. Polymorphic. We can substitute any type for M in later stages and make our implementations polymorphic. The example that I was giving you, we will see more of such examples later, that we could implement effect either with cat's effect IO or with Monix eval task or with Scala task. And we want to leave this decision back to the user. This is one of the advanced concepts. If you keep your types parametric, in that case, you get some theorems for free. For example, you can look at a bunch of types and you can deduce a lot of theorems for your abstractions. You can look at this paper from Phil Wadler for more details. But it's also one of the things which help us in equational reasoning of abstractions. Here's an example. If you write a function, suppose you have written a function which does some fold over a data structure. It doesn't do anything else. So it's always better to design the contract of the function with a foldable rather than a list. Because the foldable is a more generic abstraction, it has lesser number of possible implementations. The contract of foldable is much more general. So the implementation cannot assume a lot, cannot assume any specific constraints that list imposes. So it's always better to use the least powerful abstraction that you need. Now that we have an algebra for this account repository, what about the implementation? We can have a sample implementation like this. And the point to note here is that the implementation is also parametric. We have not yet committed to any specific instance of the effect type. It's still M, but we have added an additional constraint on the implementation. We want M to be a monad. We want to handle the errors that arise out of the APIs using the abstraction of monad error, which implies that we need to have a monad instance for M. So we have imposed some constraints, but not much. We haven't yet committed to any specific data type for M. This is important to keep your abstractions as parametric as possible. Now, here's the advantage. Since we kept M polymorphic, since we kept our abstractions parametric, we can substitute it with multiple types in the actual program that we are writing. We can use cat's effect IO and instantiate our repository using the IO monad, or we can use Monix eval task and we can instantiate the abstraction using task. So what are the takeaways from this simple exercise? We have seen an artifact of a domain model, a repository, which is parametric and effectful. A completely parametric algebra with effectful functions, a referentially transparent implementation where the effect is constrained to a monad. Remember, all the APIs return IO or Monix eval task. It returns M, which is a value. So we haven't yet submitted to the runtime system. It's still a value. So the implementation is also completely referentially transparent. We will see more details of this implementation later on in the presentation. It can be used polymorphically with multiple specializations of the effect type. We have seen this example with IO and task. And it's modular. can be tested in isolation and can be composed with other domain model artifacts, as we will see shortly. So testability is another interesting aspect when we design parametric models. Since we have minimum assumption regarding the concrete type, testability is easy. It makes our models more easily testable. For example, in our case, for the account repository, in memory, we can write tests by just using a mutable map to model the database, and we can use the simplest monad, the ID monad, identity monad. For testing, we may not need any complicated monad. Since we have generalized on the abstraction, we have not committed to any specific abstraction as part of the implementation. We can use the simplest abstraction that can fit our contract as part of testing. So we have seen a repository abstraction and how we can implement it in a parametric and yet effectful way. Now, one of the important things and one of the powerful things using composable abstractions is that we can compose these abstractions into larger ones. And this we do by composition of algebras across domain model artifacts. For example, model elements don't stay in isolation. It's not that a model will only consist of repositories. Repositories are not standalone artifacts in your domain model. Repositories need to interact with domain services. And usually the services use the contracts of the repositories to fetch data from the underlying data store and perform its own job. So there's an interaction, there's a composition between the services and the repository abstraction. And needless to mention that since our repository is effectful, we need to have the services also as effectful, and we need to ensure that those two effects align together. We cannot have different effects across services and repositories. Those two effects need to compose, because when you invoke a method of a repository from within a service, you get back an effect. So that effect needs to gel well with the implementation of your services. And this is what we call effect composition. So effects compose when algebras compose. Once again, everything is algebraic, starting from the types. So our effect is also algebraic. It has every effect, every concrete effect type obeys a certain number of algebraic laws. And effects will compose only when the algebras compose based on those laws. And algebras compose through types. So our next step will be to design an algebra for a domain service that will compose with the account repository algebra, which means the same effect needs to be propagated down from the repository to the service module. And this is what we call effectful function composition. Here's a simple intuition. This is plain old function composition. It's a category diagram. But what it illustrates is that when we have types A and B, and we have a function from A to B, function f from A to B, and we have a function g from B to C. In that case, we can compose these two functions using and then, some combinator like and then, f and then g. So we first execute f, and on the return type of f, return value of f, we invoke g. Now, it would be nice if we can translate this same paradigm to the effectful world. For example, it would be nice if we could do this. Our function is no longer a pure one. It's from A to B. It's an effectful one. It's pure, but it's effectful. A to FB. So this F stuff is there. And ordinarily, it will not compose with something which gives us an FC from B. So A to FB and B to FC. This F stuff is becoming a little pesky. We can't say we can't compose it like ordinary functions. Note that in the earlier slide, we had the identity here as part of identity which gives identity function which gives the same type as the input. And in the effectful world, we call it the pure. What we are doing is we are lifting a pure value in the context of an effect. So it's A to FA. we are given a pure value A, and we are lifting it into the context of an abstraction, into the context of the effect F. So we have A to FA. Similarly, we have B to FB. But at the end of the day, we need some combinator which allows us to compose effectful functions. Now there's an abstraction for that. We call it the Kleisli. The name is not important. And just like we say that any problem in computer science can be solved by adding another level of indirection. So here, Kleisli is just an indirection, is just a wrapper on top of the function application. It is a wrapper on top of A to FB. And the challenge is to implement an and-then combinator as part of Kleisli, which will allow me to compose A to FB and B to FC, and give me a Kleisli FAC, which is really A to FC. So this is exactly what our previous category diagram was telling us, that we want to compose A to FB with B to FC and get back an A to FC. But how to do this? We have a Kleisli, we have this run A to FB, and we can try to make one more Kleisli out of it. We have an A, we run A, which will give me an FB, right? Because run takes an A and gives me an FB. So we now have an FB, and then takes a B to FC. So we have an FB and we have a B to FC, and we want to have FC. Does this sound familiar? This is one of the common patterns which is there also in part of the Scala library. May not be in this generic form, but we have a list B, and we have a B to list C, and we need to have a list C. Yes, it's the flat map. So we can invoke flat map on F, but in order to invoke flat map, we need to have an additional constraint. F needs to have a monad. So the additional constraint that we impose here is that we can compose effectful functions when the effect is a monad. So we have this and then combinator, which gives us this ability to compose. Now let's see how we can use this. And Kleisli also gives us, Kleisli is also a monad. So Kleisli also has its own flat map, so that when we have abstractions that return Kleisli, we can compose them in a monadic way. And this is a sample implementation, a simplified implementation of the flat map combinator of Kleisli. We'll see examples of how to compose Kleisli abstractions very shortly. So now that we have an idea of how to compose effectful functions, let's take a look at a sample algebra for domain service. As I was telling, the domain service needs to take an account repository as input, and then it needs to do its job using the account repository, using fetching data from the database, and finally it returns you an account, the account which you opened. And that's also an effectful operation. So it takes an account repository M and gives you back an M account, where M is the effect type. Note that the effect type matches between the repository and the account service. And this matching will be enforced by the type system itself, since we are using the same parameter for both the effect types. And the return type is nothing but a Kleisli. Kleisli M account repository M A. The way to interpret it is that it takes an account repository M and returns me an MA. So it's Kleisli M account repository M and account for this specific UI, for this specific API. Here comes an implementation, a sample implementation of our open function. The details of the implementation is not important. What is important is to see what constraints we impose here. Remember, our implementation also needs to be parametric, and we have done that. We are still dealing with the M world. We haven't yet committed to any specific monad or specific effect type. We just have this constraint that there needs to be a monad for this M. And so we can make use of this monad error for error handling. And if you look at the implementation details, We are using a flat map here. This flat map comes from the monad. We are not using any specific type-specific information for M because we don't have it, right? So this repo.query number, it returns me an effectful query. It has an effectful return type, and we are doing a flat map on that effect because that effect is monadic. We can use raise error, which is part of the contract that monad error gives me. We use raise error from monad error to handle the exceptions, to handle the errors that can happen as part of this service implementation. So this implementation is completely generic with respect to M, with the additional constraint that M is a monad. And one thing to realize is that M being a monad is just a denotation which makes sense in the current context. You could, for some other context, you could use a different denotation as well. For example, applicative. You could use applicative. So now what our model achieves, we have now successfully composed a repository as well as a domain service. And yet we are still dealing in the value land. We are still in the pure land, referentially transparent land. Excuse me. So now we have a parametric and effectful algebra of the service that composes with the effect of the repository. An implementation that uses the constraints of the algebra of the effect type used. And the important thing is that it's still independent of any concrete effect type. The denotation of the effect that we use is monadic, with Kleisli arrows for effectful function composition. And the service methods compose through flat map. As I was mentioning, Kleisli also is a monad. Kleisli also gives you the flat map. So functions that return Kleisli, you can compose them using monad comprehensions. We will see examples. And what this model is not, we have not wed to any specific concrete type. So the implementation is still polymorphic. We can reuse the implementation with various values of M and under different context. We don't have any side effects so far in the implementation. Remember, we are done with the complete implementation of the service, and yet we don't have any side effects. The return types of every API is still a pure referentially transparent value. We are just building up abstractions for composition. We are building up the recipe, as I used to say. And in the initial part of the presentation, I was talking about some container type. Here, Kleisli is the one which lifts your computation into an effect. Now, here's a sample program using our account service APIs. Note that here we have instantiated the account service with a specific type of monad, IO. And we have composed the various APIs. Say open, we open an account, we get back an account, we do some credit, we do some debit. And finally we yield something, which is the value of the account with the updated balance. So this is a complete program which will run when we submit it to the runtime system. But for the time being, it's just a recipe. And what's the return type? What's the type of res here? It's a Kleisli. So it's still a value. We have a concrete implementation of a service, and still the return type is a value. Now, as I was telling, Kleisli needs to have this account repository as an input. So we give it. Res was a Kleisli, and we submit the we feed it with a concrete instantiation of our account repository. So remember, it was M, account repository M, and account. So it takes an account repository M, which is account repository in memory IO, and it will give us an IO of account, because the concrete type of effect that we are using is IO. So what's the type of account IO? It's an IO, still a value. We still haven't yet executed it, and we still and the abstraction is still pure and referentially transparent. It's only when we execute it, we submit it to the runtime system through this API unsafe run sync, the side effects get executed. But we have already reached the end of the world. We do not want to do anything with this abstraction. We have reached the level of abstraction that we were striving for. We have reached the final abstraction in our program. And now we can submit this abstraction to the runtime system. The runtime system goes through the recipe, executes it one by one, executes all the side effects, and gives us back the value that we are trying to compute. So this is the red part, which does the side effecty thing. But the rest of the thing is all pure and referentially transparent. Now let's talk a bit about the nature of the computation that we have seen so far. I/O is an abstraction which has not yet been realized. So it's a pure value. We have told this repeatedly that we are trying to separate the execution of the computation from the specification. So this is how we can make our abstractions lazy in evaluation. Unlike Scala concurrent future is eager by default. Future is eager evaluation. You cannot compose futures meaningfully because the moment you execute a future, it gets executed. There is no concept of this separation of computation between the specification and the execution. I/O is a monad, and hence it allows composition through flat map. This we saw. This is one other interesting thing. When you use an abstract type, the more abstract your type is, the more power you can get out of it in the later stages of your execution. I/O lets you defer the choice of execution strategy. We have mentioned that I/O will somehow manage the execution part and return us the value. Now, how it executes depends on you. For example, you can choose your own execution strategy with I/O. This we saw earlier. Calling this unsafe run sync, it will produce the result by running the encapsulated effects as impure side effects. It's a blocking call. It will block and it will give you the result. But you may choose to be async. In that case, you call unsafe run async on your I/O and pass a callback. You can decide to convert your I/O to a future. So the idea is that once again, one level of polymorphism here. You can be polymorphic with respect to your execution strategy. And the degree of polymorphism depends on the capabilities which your effect type offers. Here, I/O gives you all these combinators. I/O gives you all these various ways of executing your program. And you can defer the choice of it till the end of the world. For the same I/O, in some part of your code, you may choose to be blocking, while in some part you can choose to be async. So I/O gives you the flexibility. I/O gives you the choice. So what are the takeaways? Modules compose when algebras compose. We have seen the modules, the repository and service. They compose together because the algebras compose, which in turn means that the effects also compose because both of them were effectful modules. Effects are algebraic. We saw that. Effectful designs are referentially transparent till you submit to the runtime system. We saw that. And account service uses account repository through dependency injection, which is the Kleisli. Now, note that we have used the design pattern without making a real fuss of it. In earlier days, when we used to write, we even started to use some frameworks for dependency injection pattern, right? If you are into pure functional programming, you can just simply use the reader monad or the Kleisli abstraction to do dependency injection. And it's almost part of the standard library. Now, domain services are not alone. When we talk about, just like we talked about a repository and a service, multiple services may need to be composed as well. So now the question is, how can we compose many such effectful services in a referentially transparent way? Once again, the solution is to resort to composition of effects and algebras. Now, here's another service, reporting service, which gives you a report of the balance by account. For every account, what is the end of the day balance or end of the month balance? And there's a function called balance by account, which again returns a Kleisli, and which takes the account repository. It goes through all the accounts, and it creates a list of the balance for every account, maybe grouped by account number. it's extremely easy to compose this service with our account service because the algebras align. We are using effects, we are using algebras that align together. So note here we have invoked balance by account in the same monad comprehension as the services, as the APIs of the account services. So we open an account, we do a credit, and then we ask for a balance by account. So it will fetch the balances for all the accounts. And now we submit it to the, now we give it the repository, and we get our list. So this not only composes the repository with a service, but we can also have composition amongst services. But the criteria is that the algebras need to align, the effects need to align. And talking about polymorphism, this entire thing, your entire program remains the same. You can change only the effect. We have the same program running under a different effect. We are using the task effect type here. So it's the flexibility that matters. It's the degrees of freedom. It's the degrees of independence that such an abstraction oriented design gives it to you. The moment you separate the pure part, the referentially transparent part, or the so-called recipe from the actual execution of it, you open up a world of possibilities where you can vary each of the degrees based on your own requirement. So in summary, we have defined the algebra with parametric effect type. We have implemented with constraints of effect type being monadic or applicative. We can compose with other algebras and do the specialization in the final program. And that's fun. How are we doing with the time? Because I have a few more slides to cover and some of the advanced stuff.
Hey, I think we're good for time, so you can keep going for a little bit.
Okay.
How long do you think the rest of it will take?
Yeah, I think it will take around 5 to 7 minutes.
Oh, that's fine. Go ahead.
Okay. Okay. So this is one of the things that you need to keep in mind when designing abstractions on the JVM with effect types. Remember, we used Kleisli, right? Kleisli is isomorphic to reader T, and many implementations implement Kleisli in terms of the reader transformer, which is a monad transformer. Monads in general, they do not compose with each other. It's not a generic offering, but some monads do compose. And for others, you need to define transformers. Monad transformers is a way to stack one monad on top of the other, so that finally you get the effect of all the monads together. So Kleisli is reader T, reader transformer, and we have already seen that M also needs to have a monad type. So already we are talking about two monads. Reader T will compose with our M type. Similarly, in our implementation, we talked about only the M type. But as part of your API, you may be dealing with other monads as well. For example, we may use either T in order to handle exceptions. Either is a very common way to handle exceptions. So you need to use either transformer in order to integrate with the rest of your monad transformer stack. So this way you can build quite a sizable amount of monad transformer stacks as part of your API design. This is possibly okay in Haskell, but not on the JVM. On the JVM, monad transformers do not perform well. There are lots of reasons for this. The primary reason being there are lots of allocations on the heap, and the JVM will literally cry with a fairly deep monad transformer stack. And also there will be some megamorphic dispatches of function calls, as the JVM will struggle to find the most concrete monad implementation that we need. This is related to some of the internals, and more such details are there in this John Ghosh article that I linked to here. It explains very beautifully why monad transformer is not a solution, at least on the JVM. So what's the alternative? Can we do better? Type classes is the answer. For every monad that we use, we can have a type class. For example, for the state monad, we can have monad state. For the reader, we have an applicative ask. And all these are part of the libraries which we have. For example, CATS has all the implementations of this. Scala Z also has them. Also has all of these implementations. So instead of fusing monad transformers one on top of the other, we can have smaller grained effects modeled as type classes, so that you don't have to deal with the entire stack and have pressure on your heap and let the JVM decide which monad, how to unroll those transformer stacks, and use hand-rolled instances of the type classes specific for your application. There's a library called Monad Transformer Library. The name is a bit of a misnomer. There is no transformer as part of MTL, but it has some historical connotations why it's named like this. But the Monad Transformer Library in CATS or in Scala Z gives you the facility of these type classes, small type classes, which you can use as part of your domain model design instead of dealing with large monad transformer stacks. Now, here's an example. We have re-implemented the open API of the account service using the monad transformer library, using MTL. So no more Kleisli. So open now returns only the effect. And as part of the implementation, we are handling all of the functionality using the type classes, which we use on the top to constrain our abstraction. We had the monad error. Monad error is also a type class. And note that here monad error is parameterized on app exception. That's a custom exception for the application. And we need to provide a hand-rolled instance of monad error. And believe me, it's not difficult. Monad error is a very small type class. In fact, the basic idea of coming up with this type class approach for every monad is to make them smaller. All of them are fine-grained and all of them have maximum 2 to 3 methods to implement. Applicative ask. Applicative ask is the replacement for the Kleisli. Applicative ask has an ask method, which when you instantiate applicative ask for account repository and you ask for it, it will give you back the repo. So no more you need to handle it as part of your return type and add it to your monad transformer stack. So it's one other constraint which we add as part of our implementation. But the implementation becomes much more simpler, and most of all, it becomes performant. So this is a simplified view of applicative ask. It has this ask method. It has a couple of other methods which I don't remember offhand. And this is our algebra for account service. Do you note any similarity? In both of these, we have the effect types parameterized. So applicative ask is also a parametric API. And account service also gives you parametric APIs. And both of them are parameterized on the type of effect. So when you do ask a.ask as we did in the earlier slide, so you get back the exact effect which you pass in, to which you constrain your implementation. And this style of design is called the tagless final, where you parameterize your effects and you have functions for each of your algebras. Tagless final, the term I think was coined by Oleg, and if you search for tagless final in Google, you will get a bunch of references from Oleg, and it explains the concept and how it differs from the initial implementation. You can see that. So here are some of the final takeaways. Use parametricity. This is possibly the most important advice as far as abstraction design is concerned. Never make your abstractions concrete upfront. Type constructors for modeling effects, as we just saw. Compose with values. Pure values compose, and referentially transparent values compose. And composition also takes place in the presence of effects. And this is another very interesting advice and very important advice is to ensure a separation between the specification of the abstraction and the execution part of it. Use the above principles to where domain artifacts. Keep in mind all of these above 4 advices when you design your domain artifacts. Thread through domain behaviors using the selected denotation. Constrain the denotation as part of your implementation, and use that denotation to thread the effects through the domain behaviors. Avoid monad transformers, just as we saw. Use type classes for smaller grained effects, as we saw with applicative ask and monad error. Roll out hand-rolled instances of type classes. This should not be difficult, but it makes a world of difference as far as performance is concerned. Be lawful. This is one thing which I didn't discuss much, but all of these abstractions like the monads, the applicatives, and things like that, they all have algebraic laws. So write tests, write your test suite to verify that the abstractions that you design, if they have any of these denotations, they obey the laws, because the laws are not enforced by the type system, at least not till date, and not in Scala. This is an interesting quotation which I found. It was from Rob Norris in last year's Scale by the Bay talk. Effects and side effects are not the same thing. Effects are good, side effects are bugs. This is a very strong statement. Their lexical similarity is really unfortunate because people often conflate the two ideas. And the basic idea behind this presentation is to prevent this conflation. Effects are algebraic. You need to use effects in order to address side effects. And in case you are interested, I discuss many of these things in one of my books, which was published a couple of years back. So functional and reactive domain modeling, it discusses the basic principles of functional programming with using Scala Z, because CATS was not there in the current form at that point in time. So that's it. Thanks a lot for coming, and any questions? Or do we have questions? Yeah.
Yeah, thanks a lot, Debasish. I'm sure there's questions. I don't have the remote microphone working, so if you could come up and close to the computer and ask your question if you have one.
Or I have my email address, so in case anyone has any afterthoughts, any questions later on, you can always she can always fire me an email.
Yeah, we got a question.
Yeah, sure.
Hi. My question is, how do you do fine-grained error handling with this effect system?
Fine-grained means it depends what you mean by fine-grained, but yeah, if you want to handle it at the effect level, then you can use abstractions like monad error. You can use monad error to handle errors. By errors, I mean the domain-specific errors, not the catastrophic exceptions.
Hey, Debasish, thanks for the talk. I was wondering what your opinion is on integrating errors right into the effect system, like BIO or like ZIO. Like, what's your opinion of that, rather than sort of using, two sets of effects?
Yeah, actually, I think I haven't looked into Scala Z IO in details, the recent one which John Digos has implemented, but I think there's a difference of philosophy between the two libraries, CATS and Scala Z IO. Scala Z IO assumes that there will not be any errors. There will not be any errors means it doesn't take into account that exceptions may arise besides the catastrophic runtime ones. So so every API of Scala Z IO, you will see that it's based on the concept of purity, whereas CATS effect takes a slightly different approach. Possibly it comes from Monix as well, that they have the provision for handling errors through exceptions as well. So it depends on how much pure you can afford to go, but on JVM, I find the pathway taken by CATS is a much more realistic one. because in reality you can't avoid exceptions, particularly in view of the fact that you need to integrate with many of the underlying Java libraries. So I'm personally I think that having a provision for exceptions is a good way forward. It's more of a pragmatic decision, but it should work on the JVM like that.
I actually have a follow-up to that, if that's okay.
Yeah.
So the thing is that I actually asked Chandraghosh about this a while back, and he mentioned that what ZIO does is it has a limited set of error types which you can handle in any given action. But if there's an exception outside of that range, then it pushes it up to the fiber supervisor and lets it deal with it.
Right. Yeah, it's a question of philosophy. He has decided to design it like that, and I'm sure it's more aligned to what the purists will suggest, pure functional programmers would suggest. But as we know that JVM is not really a pure functional programming in a platform, so it has its own limitations, and it was not designed like that. So you can try to be pragmatic or you can try to be idealistic, but yeah, it's a matter of choice.
Hey, Debasish. It's really interesting talk. It demystified some of the stuff that I see on the internet, and I don't understand how to read it. So one of the things that I really liked is how the idea that you defer the execution of the side effect or the effect in this sense, but staying pragmatic with the other team members that not necessarily have heard your talk. Could it be like you talked a lot about a lot of different things? If I take only one concept, which is deferring the execution till the very end, would it work, or I need to take the whole system? It's like it's all or nothing, or I can actually use only some of it and gain, and it will work.
Yeah, I think what I discussed are a lot of topics. So yeah, that's one of the most fundamental things that I wanted to drive home. Designing abstractions that give you this separation. And unfortunately, the Scala concurrent future is not like that. The default implementation of Scala concurrent future is by default eager. Whereas if you go through the libraries of Haskell, most of the abstractions are lazy by default. And laziness wins in most of the cases because lazy abstractions are easier to compose. So once you have a separation between the creation of the recipe of your abstraction and executing it, I consider it to be one of the best practices, and I try to follow myself also that same practice in all abstractions which I design. So because of that only, I prefer Scala as I prefer Cat's Effect IO over using something related to futures.
Okay, thank you.
Okay, I think that's it, Debasish.
Okay. Thanks, Sean, for calling me. It was a pleasure.
Oh, thanks a lot for accommodating us. I know it's a very early hour over there.
Oh, that's okay. I'm used to it.
All right, I'll talk to you soon.
Yeah, sure. Thanks, Sean.
Bye.
Bye.